In this video, we'll talk about spontaneity, entropy, and isothermal compression and isothermal expansion. Okay, so I would like to keep this video as short as possible. So I would explain about what is the most important part. Okay, so the first thing about this chapter is spontaneous process. Okay, notice that the first thing I think you already have learned from the class that the first thing you will learn about spontaneity is that if the reaction is spontaneous, then the entropy should be increased to a larger state, in the larger value, which means that if one reaction is spontaneous, then the degree of chaos 乱度 should be more higher when the reaction is finished. Okay, so let's review a little bit more about this. About spontaneous process, the all we concerned about is will it happen or not? Well, it happened. We do not care about if this fast or if it's this slow. So take example, if you put the sodium metal 钠金属 and you put the sodium metal inside of water, what will happen? It will explode and it will cause fire. But so this is very obvious that this is spontaneous. But later on, if you put bread on the table, and what happened? It will grow mold. 会发霉. It will grow mold on it. It is much more slower than the sodium put inside the water, but although this is still spontaneous. So there's a difference in speed, but the spontaneity is always spontaneous in this two reaction. Okay, they tell us the direction of a reaction, but we can say nothing about the speed of the process. Okay, because this is a thermodynamics. All we concern is the initial state and the final state. If we want to concern about the speed, it is come to kinetics, which will be will be the contents in the later chapters. Okay, thermodynamics consider only the initial and final state. Okay, doesn't consider the pathway. So, review from the beginning of thermochemistry and thermodynamics to this part, we have already learned that heat and work are not a state function. So you have to consider the path that we have gone through. But enthalpy, internal energy, and later on we will meet entropy and Gibbs free energy. And in a sophomore year, we might meet Helmholtz free energy, which is not important in general chemistry. These four energy are state function. We all need to consider is the final state and the initial state. Okay. Okay, characteristic common to all spontaneous process is increase in entropy. Okay, change in entropy is a measure of the driving force. Okay, actually, in entropy, if we speak in Chinese, it will be translated as 乱度, which means degrees of chaos, or you can say, how messed up are you? Okay, so this is kind of easy to understand. So let's take a little bit example. So imagine this. When you're going inside of the bathroom and somebody just, I don't know, maybe he just poop or he just urinate. Okay, so the bathroom should be smelly, or you can say stink, 会臭臭的, it stink. So, why would you smell the scent of those molecules from the urine or from those poops? Because the molecules of the poops just come into your nose and stick onto your nose and trigger your nerves that your brain can feel that the smell has come into your nose. But is there any possibility that you go to the bathroom and smell nothing? Yes, of course. Okay, imagine this. Here's a toilet, and you walk inside of this, and here is some maybe poops. Yeah, I'm not gonna say the S word, the S word. I'm not gonna say that. Okay, there's some poop inside of here, and there are some molecule that causes the smell. Okay, is there any possible that all of the molecules stick over here but do not go over here? Of course, there's a possible that this will happen, but uh, you can know that the probability is very low. Okay, so let's do this again. Let's draw two bars. Okay, imagine there are molecules over here. The amount is approximately, I don't know, I don't have the count this. Okay, approximately like this. Is this possible that the state that all of the gas molecules stay inside of this bubble? Yes, there is a possibility, but will it happen in the normal state? Of course. It's common sense that this should not happen. But what is the most likely thing to happen is like they are equal. They are equal molecules in both sides. So this state over here comes to this state over here should we call spontaneous because this is natural for the gas to flow like this. Okay, so the entropy over here should be higher, and the entropy over here should be lower. Why? Because all of the molecules stay in the same place. Isn't that less chaotic or less messy? Yes, but if it comes from here to here, what does it mean? It means that you go here, you go here, you go here, you go here, you go here. It's so messed up. So this is messed up. You're more likely to be like this. Okay. Okay, so imagine another thing like this. When you go to a new room, maybe you come to NTHU and you move into your dormitory, and what will happen? Because you're new into the dormitory, so the initial state is the table should be completely empty. Is reasonable, right? Completely empty. Okay, and after you stay in the dormitory for a little bit time, maybe 1 month, 2 months, or 3 months, then later on you put some stuff on your table, and as long as time goes by, you put more and more stuff on your table, and because you're busy and you do not have time to manage the tidiness of your table, so your table will become more messed up because you do not put any effort on tidying up. So, okay, because you don't tidy up, means that you just let this happen. You just make things go naturally. So, if you do not put any effort on tidying up your table will be more messed up. So this is the natural flow. So we call this spontaneous. Okay, I think after explaining like this, you will have the idea of spontaneity. Okay, so let's take a look example that is put inside the textbook. Okay, so I'll walk you through here this very quickly. Okay, imagine there are two bulbs over here. Bulbs 就是球. Okay, there are two bulbs over here, and A and B, there are only two gas molecule in the system. Okay, this is very simple. We manage the situation to be very simple. Okay, what is the microstate? Or we can say that how many possibilities that the gas molecule can arrange. Okay, so let's take a look over here. A and B two. There are two kinds of possibility. One is A and B are here. O and B are here. Or A and B are all here. Or A here, B here. Or B here, A here. Okay, is that correct? Okay, so actually I didn't write this correct. This is the omega is the probability of state, the numbers of probability of state. So it should be like 4. One is all here, one is all here, one is one here, another is here, and one is here, and one is here. Okay, okay, okay. Walk through if the possibility becomes 4 over here. I'm sorry, if the numbers of molecules become 4 over here, the possibilities of arrangement is like 4 over here, or 4 over here. All 4 is here. Oh, all 4 are here, or all 4 are in the left-hand side. Okay, so later on, if we put 1 to the left, sorry, we put 1 into the right. There are 4 possibilities because you can choose A to be here, or choose B to be here, or choose C to be here, or choose D to be here. Okay, later on, if you put 2 inside of this, you can put AB, you can put AC, you can put AD, you can put BC, you can put BD, or you can put CD. This is just arrangement. I think Taiwanese students should be very familiar in their high school mathematics. Okay, okay. If you put 3 over here, it will be the same as you put 1 over here. Is that clear? Okay, again, you put 1 over here in the right hand side. Should be the same arrangement, numbers of arrangement to put 1 in the left hand side. Okay, so here we have 4 possibilities. Okay, so all of these added together, then we will have 16 possible states over here. Okay, so let's see over here. The arrangement, you can see the amount of arrangement will have the maximum amount when 2 over here and 2 over here. And does it looks familiar with you? Because you know, 1 over here and 1 over here is the maximum arrangement in the scenario of 2 molecule of gas. Because you know, all of molecule over here or all of molecule over here only have 1 and 1 state. But over here, you have 6, and this is 4. This is 1, 4, 1. So we can see that in these two scenarios that it will tend to be equal amount in 2 bulbs. Okay, so let's take a look in the probability. I take it from somebody's PPT slide over here. So if there are 2 molecules in the system, it should be the probability of 2 over in the left-hand side should be approximately 0.2 something. And the probability of 2 molecules are all in the right-hand side is the same amount of 2, all 2 in the left-hand side. And we can see that when, because this the total amount is 2, when one ball in the left hand side and 1 ball in the right hand side, we can see that the possibility should will meet the highest amount over here. Okay, and from the chart over here, we can see that this is tends to be like a normal distribution. Okay, so as the number of the balls becomes more and more, the experiment will be more precise. Okay, is that clear? So when we have 10,000 of balls, and the distribution will be very clear that it will tend to have 5,000 over here and 5,000 over here. So when it's equal amount, it will reach the highest possibility. Okay, so over here we can see, is there any chance that all of the 10,000 balls molecules can be in the same site? Yes, there is, but the possibility is very small. So let's go back to the man in the toilet. So the gas molecules will be tended to flow in all of the space it can go. All right. Okay. Is that clear enough? So and when we talked about spontaneity, is actually when we discussed about what is likely to make this, what is likely the pathway that this reaction can happen. Okay, this part should be over. And when we talk about we will continue to talk about spontaneity when we talk about entropy. This is more likely to explain the chemistry by mathematics, because you know, although we demonstrate this story in a very in a very dramatic way, I think you can understand what is the show is going on. But I think, you know, scientists are like paranoid, and you cannot just say that this will happen, this will happen. So what is the best way to prove a thing will happen? Use mathematics, use numbers, use statistic. So later on, we'll use entropy to explain the spontaneity. And okay, Okay, let's go to the